3.13. It is to show that the power of the signal, x of n, which is given as d e to the j 2 pi times n is d squared. Okay, so it's not like this. Here's the signal. I don't know what we meant by the first part, but the signal is r goes 0, 0 minus 1, dr e to the j r times 2 pi over n 0 times n. And it says here, determine the power of this signal. And this is, I guess this signal exists only over, I guess it exists for every n. This is a periodic signal, right? This signal is periodic. What is the period? The period of this signal is n 0. So, how do we approach this problem in general? Well, we say that the power of the signal x is going to be sum over, or I should say in general case, limit when n 0 goes to infinity, 1 over, or let's say n goes to infinity, 1 over 2n plus 1, sum of x of n magnitude squared when n goes from minus n to capital N. This was our definition of the power in the general case for any signal. Now, if the signal is periodic, we don't have to, just like in the case of the continuous, integrate over the entire axis. We just integrate over one period. In this case, the signal is obviously periodic. The period n0, because every n0 loops around for 2 pi. So you kind of exponential is periodic with a period of 2 pi. So now the power of this signal becomes 1 over n0, which is 1 over the period, and then sum when n goes from, or this, let me just make sure that x, so this x of n from x, okay. So n goes from 0 to n minus 1 in over one period, x of n magnitude squared. All right? So this is what we need to sum. So if I now substitute, if this is x of n, so here's what I need to do. I need to put this summation in here, square it, and then evaluate this sum. All right. So let's do that. So this becomes 1 over n0 sum n goes from 0 to n minus 1, and then I have to take the magnitude of sum when r goes from 0 to n0 minus 1, dr e to the j r 2 pi over n0 times n squared. Okay? So that's what I need to evaluate. Now, that's where you have to kind of have a little bit of skill in doing this math. What we covered some time ago is that z magnitude squared can be written as z times z complex conjugate. Right? This is a very common expression that we use. So let's use that in here. I'm going to say that the power of this signal becomes 1 over n0. And then there's first sum over n. It goes from 0 to n minus 1. And I'm going to have the second sum over r. R goes from 0 to n0 minus 1. dr e to the j r 2 pi n over n0. And then times the third sum, let's say nu goes 0 and minus 1, d nu e to the minus j nu 2 pi n over n0. That's pretty crammed here at the very But you realize what this part is. This is my x of n, right? If you look at it from here, this is x of n. This is also x of n, but take the complex conjugate. And the product of x of n complex conjugate is magnitude of x of n squared, right? So now we have, I don't know if these dRs are complex. Yeah, they are. So this is also complex conjugate. Now, like in many of the problems of this nature, you try to find a way how you jumble this so that it simplifies. In other words, change the order of summation. So instead of summing over n last, let me try to sum over n first. So it becomes sum when r goes from 0 to n0 minus 1. And then sum when nu goes from 0 to n minus 1. dr times d nu complex conjugate. And then I have an interesting term here. Sum when n goes from 0 to n0 minus 1. E to the j, let me put here 2 pi n over n0 r minus nu. Okay? So now, let's look at this term here. I'm summing exponentials. N goes from n0 to n, so I have n0 terms here. Let's say when r is different than nu. So this is some sort of integer, right? So let's say r is different than nu, case 1. Let's just look at that term. Sum when n is equal to 0, n0 minus 1, e to the j 2 pi r minus nu times n over n0. When first case, so let me call this sum Sn. Case 1, let's just actually look at easier case. Case 1, r is equal to nu. That's an easier case. If r is equal to nu, then what is this? This is 0. E to the j0 is 1. So the value, you have n0 terms, each one of them equal to 1. So the value of this summation is what?
N0.
N0. So in this case, Sn is equal to N0. Let's look at the different case. Case 2, now when nu is different than r. When nu is different than r, then you have an integer number here, right? That is being added. So you have, let's call nu minus r equal to some k. So our Sn becomes sum when n equals 0 to n0 minus 1 e to the j 2 pi k n over n0, right? For this case, some integer. The easiest way to see how this sums is to do this. Well, let me just unwrap this a little bit, just so that I understand what is it that I'm summing. So I have e to the j 2 pi k times 0 over n0 plus e to the j 2 pi k times 1 over n0 plus and so on plus e to the j 2 pi k times n0 minus 1 over n0. okay? And he gives you here that this is equal to 0. But how do we prove that? I don't see it right away. Maybe one of you can see it.
I think there's a hint that helps out.
No, he gives you flat out that this is equal to 0. But the proof of that escapes me right now. Right? So let me see if I can think of it. The only thing that comes to mind is, let me call that this may lead us to dead end. So let me just call this J2 pi k over n0r. So then this Sn becomes r to the 0 plus r to the 1 plus and so on plus r to the n0 minus 1, right? And I know how to sum this, right? This is 1 minus r to the n0 over 1 minus r, right? This is the geometric progression. So let's substitute that in here. So this becomes 1 minus r to the n0, r is this. So this becomes e to the j 2 pi k times n0 over n0 divided 1 minus e to the j 2 pi k over n0. Beautiful. So what is this? n0 and n0 cancels. E to the j 2 pi times integer is 1. So what is the value of this? 0. So beautiful. So this is equal to 0. So now we have a beautiful result that this Sn is equal to n0, where nu is equal to r. I'm kind of reusing letters. Maybe we call this z, right? So that it's different than what r over there. So z, right? And now it doesn't matter, but when you go back and look at the notes, it better be different, right? So now we have a beautiful result that this is equal to n0, where nu is equal to r, and 0 when nu is different than r. So that's this portion here. So now I have a double summation here, right? If I were to draw this summation, here's how on a plane, this is how it would work. This is where your r advances, this is where your nu advances. So 0, 1, all the way to n0, 0, 1, all the way to n0. So this gives me n0 times n0 terms, this double summation, right? I have r goes from 0 to n minus 1, and nu goes from 0 to n minus 1. So for every combination r and nu, I have a term that I need to add, right? You follow so far?
Not that far.
Well, look at this summation. How many terms are here? Let's call this one term. That's a term, right? So r goes from 0 to 0 minus 1. Nu goes from 0 to n minus 1. So you have n0 terms based on r, and n0 terms based on nu. So you have n0 squared, right? R goes from 0 to n minus 1, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. 2, 1, 2, 2, 2, 2, 3, 2, 5, right? So you have n0 times n0 terms. But an interesting thing is, whenever r is different than nu, this part becomes 0. So it gets rid of it. So even though, formally I'm summing across this entire square matrix, the only terms that matter are the ones that are on the main diagonal. Because only for those terms, this summation here, Sn, is different than 0. And I have the value, it is equal to exactly n0. So this double summation now becomes, which is our power, px. I'm just going to sum over nu, and it's going to be d nu times d nu complex conjugate. Let me put 1 over n0 up front. And then since nu is equal to r, the value of this sum, Sn, is equal to n0. Right, this is this Sn. This guy here, this third summation is equal to n0 because I'm just moving across the main diagonal of this matrix. Okay? So far, so good? And then you can see what happens. This n0 and n0 cancels. D nu times D nu complex conjugate is the magnitude of D nu. So you end up saying the power of this signal is sum when nu goes from 0 to n0 minus 1, D nu magnitude squared. That's what we want you to put. Okay? Okay. Good, this is a nice problem. Nice problem. It refreshes a lot of stuff that you should have seen a long time ago. Right? But this is, you know, and it's not purely mathematical problem. What you will see, we'll come back to this thing. And this is your, like a prelude to the discrete Fourier transform. Right? So that's where the, you know, out of something like this is where the discrete Fourier transform is going to come up. Okay. All right, so if you're wondering why I'm drinking out of this pink cup in my throat, I have these allergies that make me cough so much, so hopefully this will help. All right. So last time we talked about discrete time systems, and towards the end, I said something like discrete time systems can be represented with difference equations. Just what differential equations are for continuous time systems, the same role is played with the difference equations. Difference equations are of this form: y of n plus n plus, this should be squared, okay? A1 y of n plus n minus 1, and plus so on, plus an y of n is equal to b of n minus n x of n plus m plus d of n minus n, no, it's the other way around, n minus n, right? N minus m, n minus m minus 1, x of n plus n minus 1, all the way to bn x of n. Right? So what are we saying here? If we put ourselves at the time n plus n, right, that we can call this a current sample of the output, then you can see that the current sample of the output is a linear combination of past m samples of the input and past n minus 1 samples of the output in the general case. A casual causality condition requires that m is smaller or equal to n. In other words, you're saying the current output cannot depend from the inputs of the future. The causality condition we're going to limit ourselves for the most part to causal systems, but I refresh your memory again. Causal is not something that is exotic. A lot of systems are causal. Everything that we process that's non-real time can be non-causal. For example, if you do the best noise reduction algorithms are the ones which take the entire sample and then work to reduce the noise. For example, at the first sample, by knowing where this entire signal ends up. Test your understanding too. Let's say I'm speaking and I'm in the middle of the sentence, right? And there's a lot of noise on top of what I speak. Would your ability to understand what I'm speaking increase if you listen to the sentence all the way through? Yes, right? You're doing the noise filtering. So by listening to the whole sentence, you can go back and say, oh, okay, he didn't really say blue. He said, zoo or something, right? Different. Because you know that I ended up with sky, right? And zoo didn't make sense with the sky, right? So by listening to the whole signal, you can do filtering of the samples or produce the output, knowing what the inputs are going to be sometimes in the future. And the systems that are non-causal are quite common in that respect. But for this analysis here, to keep our math as simple as possible, we're going to assume for the most part that the systems are causal, so that your output depends on the past values of your input, past values of the outputs, and maybe up to the present value of the input. The equation of this type is called nth order difference equation. So this is a order difference equation. More natural way to write this would be just shifting everything by n. And a lot of books actually do it that way. They would write this y of n plus a1 y of n minus 1 plus an y of n minus n is equal to b n minus m x n minus m plus b n minus m minus 1 x of n minus m minus 1 plus and so on plus b n x of n minus m. Right, this is another way of writing it. It's more natural way of doing so. Right? And if you're taking a DSP class, probably this is the way how they write it over there. But to be consistent with the continuous world and with your textbook, I'm going to adopt the same notation here, which is really nothing big, no big deal. We're just shifting which time I call present time. Here the present time I call the nth sample. Here the present time is n plus nth sample. It's just it's arbitrary to begin with, so it's correct either way. So the question is here, how do you solve this equation? And the answer is, well, it's already solved. Unlike differential equation, which you cannot really get y of t easily. Here it's because you're walking in discrete steps, your y of n is already spelled out for you. So first way of predicting what the output is to perform the recursive evaluation of your difference equation. So let me just rewrite this. So recursive if if I take this equation star and I rewrite it in the following, or rather this double star, it's easier. I rewrite this in this following form. Y of n is equal to minus a1 y of n minus 1 minus and so on minus an y of n minus n, and then plus v n minus n x of n plus this all actually, let me just make sure. Okay, let's assume n is equal to n, which is the limiting case of a causal system. It is kind of general case too, because everything fits in this case, but some of these b's can be made 0, right? So then I have b0 plus, let's say b1 x of n minus 1, and plus and so on, plus bn x of n minus n. So I get a recursive equation that if I know my initial conditions, I can actually calculate every y of n, right? Give me some initial conditions so I can start calculation. I can code this easily, let it run, and it will produce every y of n. So in the sense of predicting the output in the case of discrete systems, this is much easier task than in the case of continuous systems. So let me work first an example so that you can get an idea what is it that I'm talking about. Let's say this is an example. This is the same as your example 3.8 in a book. It says consider a discrete system which is described with this differential equation. Y of n minus 0.5 y of n minus 1 is equal to x of n. What is the n in this case? What is n in this case?
0.5.
No, n, capital N. Look.
1.
0.
No, look at this. 1. N is equal to 1. And what is m equal to? 0, right? So I'm depending on one pass output and just the present input, right? So this is the difference equation. Now I have initial conditions. That says y of minus 1 is equal to 16, and I know that my input sequence is n squared, right? So I have the initial conditions for y, and I have my input. Can I predict what the output of this system is? And the answer is yes. All I need to do is set up a little piece of code that does this evaluation. Or if I'm, like I'm right now on the board, then I can do at least first couple of terms manually. So what you usually do, you kind of say y at the current sample is equal to 0.5 y of the previous sample and plus whatever is the next sample of the input. So you put the equation in this, what we call recursive form. And then you let the clock tick. So this is n equals 0, n equals 1, n equals 2, and so on, right? You can keep on doing this evaluation. So for y of 0, this becomes 0.5 y of minus 1 plus x of 0. So this is 0.5 y of minus 1 is equal to 16 times 16 plus 0 squared. So this is equal to 8. Y of 1 becomes 0.5 y of 0 plus x of 1, which in our case becomes 0.5 times 8 plus 1 squared. So it's 4 plus 1, 5. Y of 2 is going to be 0.5, y of 1 plus x of 2, which in this case is 0.5 times 5 plus 2 squared. So this is 2.5 plus 4, 6.5, and so on. You can proceed with this and get every value of the output. The beauty of this, I don't know if you notice it right away, the beauty of this is this would work even if my system is non-linear, right? I mean, you can, just like you have, this is a linear difference equation. You can form a non-linear difference equation that instead of having linear terms here, maybe this is b1 xn minus 1 to the power of 3, or square root of x of n minus 1, and so on. You can still do the evaluation. But what is lacking here, even though you can do the evaluation, you don't necessarily understand the dynamic of the system. Let's say I do, and it turns out in this case, that's the case. If I continue this doing, the system is going to go to infinity, right? So the question is, how do I fix that? You know, is it my input that's driving it? Is it the system dynamics itself that is driving it? And then, really, in order to do that, what we need to have is some sort of analytical solution where we have understanding of what the system is, what is inside this box. And you guess it, probably, that we're going to limit ourselves to the linear systems, and we're going to have a closed form solution for linear systems, and it's going to be very similar, it's a similar story to our continuous system. We're going to have characteristical equations, characteristical modes. We're going to have a zero input solution, zero state solution. The total is going to be sum of the two. So we have to kind of go through it and see how all of this applies in the case of a discrete system. To do that and to simplify my notation here, to be kind of consistent to what we already did for the continuous, I'm going to introduce difference operators. Difference operator. And this is E applied to x of n. So when operator E is applied to the x of n, it results in the next cent. So it shifts to the next cent. Along the same token, E applied to the x of n plus 1 is the same as E applied to the E of x of n, which is E squared applied to the x of n, which is x of n plus 2. You get an idea, right? This doesn't mean E squared times x of n, right? This, you have to treat this the same way we treat D. D just tells you what to do. It is not multiplying, it's not the constant. So along the same token, if I continue this operator e to the n applied to this x of n performs the shift by n samples. So now having this in defined, then we can take another look at our difference equation there and transform the difference equation. We can see that difference equation over there is e to the n plus a1 e to the n minus 1 plus and so on an. This entire operator operating on sequence y of n will be b0 e to the n plus and so on plus bn, just bn, right? bn operating on a sequence x to the n. Just a notational convenience, right? What I'm really meaning by this is what I have written over there, because that's a reality. This is just a shorthand notation for that reality over there. And the common way to write this, we're going to say Q of E, which is the polynomial of this operator operating on a sequence y of n, is equal to P of E operating on a sequence x of n, right? Nothing really fancy. We already seen that we have that P of D, Q of D operating on x of t. Now this is equivalent. It's just now discrete time. So let me do an example so that you see how this translates. Let's say I have a system that is described with the following difference equation: y of n plus 2 plus 1/4 y of n plus 1 plus 1/16 y of n is equal to x of n plus 2. Then if I rewrite this using operators, this is e squared because it's a 2 shift relative to y of n, plus 1/4 e plus 1/16, all operating on y of n. And then this is equal to e squared operating on x of n. We're bringing them all on the same time, and then this becomes your Q of e, and this becomes your P of e. Just to test you, what is n in this case? Capital N.
2.
How large is n?
2.
2. How large is n? 2 as well. Right? So in this case, we have n equal to n. Now, let's narrow our attention to linear systems and discuss the response of a linear system. And our goal here is not going to be the same as the goal we had in a continuous. I mean, it's going to be similar, but not exactly the same. Where do they differ? Well, unlike time domain continuous systems, here we can always calculate the output. There's no doubt about it. We can actually go through the recursive evaluation of this difference equation, and for any given input sequence, get the output sequence. What we are really looking for here is an insight in the system behavior, which we only get once we solve, obtain a closed form solution of the output based on the input. And so the response of linear time invariant discrete system. So here's our scenario. We have a box here which is linear time invariant discrete, and we are putting an input sequence x of n, and we're having an output sequence y of n. In general case, y of n, or we can say y total of n, is going to have two components. One is going to be your y0 input of n, and plus y0 state. Okay? Now, why was it important to say that this is a linear time invariant system? This is not always the case. If the system happens to be non-linear, then the superposition may not hold, and your response of the system may become some mixture of the two. Right? If I look at 0 input and 0 state, and then I put them together, it's actually going to be different than the response of the system in the non-linear case. In the linear case, however, the due to the superposition, you can see the response of the system is consisting of two parts. One part is because at the time when I declared 0, there was some energy of the system, and that will gonna inside the system, and that will ring for some time. And then the other one is the part that is excited by these inputs that will be superimposed on those outputs that I get from a 0 input case. So first thing that we're going to do is 0 input response. Now, if I look at my general difference equation, so in general, for the linear time invariant difference system, I have Q of E operating on Y of N is going to be equal to P of E operating on X of N. But since X of N is equal to 0, then difference equation that I have to solve is Q of E Y of N is equal to 0. Let's call this 0 E. Right? That's a difference equation that I have. If you look at this from a recursive evaluation, then there is a trivial solution here. Y Zi of N is equal to 0. So if your initial conditions are 0, this will never start, right? You know, Y of N is going to be a combination of past values of the output, but if the past values of the output are 0 at time N equals 0, then everything continues being 0 afterwards. So this one actually has, you can think of it as, it is started by the initial conditions, and it describes how does the output progress as a result of some non-zero initial conditions. Now if we expand on this, we can write it this way: e to the n plus a1 e to the n minus 1 plus and so on, plus an applied to 0 input of n is equal to 0. Now, remember our objective here is to solve for the general form of the solution Zi of n. And we're going to consider a solution in the form y Zi of n is going to be equal to C e, not e, gamma to n, right? Where C and gamma are to be determined. Now, if you substitute this in this equation here, you realize the following: E operating on y0 input of n is going to be C gamma n plus 1. Right? Why? Because it's shifting from n to n plus 1. But now, this can be written as gamma times C gamma to the n, and you recognize this to be gamma times y to the 0 input of n. Okay. Along the same lines, E squared operating on y0 input of n is going to be gamma squared y input of n. Okay, so we're looking for a solution of the 0 input to be this form, right? And what we're finding out, if we put this form in here, there are some special properties that are coming up. So if I now substitute this into this big equation, therefore, we have the following. Gamma to the n plus a1 gamma to the n minus 1 plus and so on, gamma, or actually just plus an, multiplying y0 input of n is equal to 0. Okay? So, we are assuming that the solution is in this form, and this assumption leads us to, it says it can be in this form, but this gamma needs to be suitably chosen. How do I choose this gamma? It needs to be a root of this polynomial, right? Why? Because this equation, it should be really, we should write it like this. It should be identically equal to 0 for every n. There are two possibilities. Why 0 input of n is equal to 0 itself, which we already discussed. This is a trivial case where there is no energy in the system. Your initial conditions are 0. Therefore, nothing ever shows up in the system. Shows up the output of the system because the system is relaxed to begin with. But if your initial conditions are different than 0, that you can make this condition work if your gammas are of a special value. And what are those special values of gamma? They need to solve this polynomial. They need to be roots of this polynomial. So for that to happen, we define something that we call characteristic polynomial. Polynomial is Q of gamma, and we define something that we call characteristic equation. Which is equation Q of gamma is equal to 0. Now, if the order of this polynomial Q of v, which we know is n, how many different gammas can I find to satisfy this?
Both.
Exactly n, right? So there are exactly n values of gamma of which Q of gamma is equal to 0. These values are called characteristic values. And in general, we have three cases. All gammas are different. Some of the gammas repeat. And then we kind of separate the third case when we say some of the gammas are complex. That's really not a different case, because if they're complex, they're all still different, right? So that kind of is a subcase of the first one, or maybe even second one, because they may be complex and repeat. But it's important for us to separate that because it leads to a different behavior in the system response. It leads to oscillatory behavior in the system response. So there are three cases. So case one, all roots, all characteristic values are real and different. So let's say gamma is from the set gamma 1, gamma 2, all the way to gamma sub n. Then your zero input response, this is getting a little, zero input response of n is in this form. C1 gamma 1 to the n plus C2 gamma 2 to the n plus and so on Cn gamma n. Sorry, this is little n. Right? So that's the form of your zero input response. Again, this, just like in the case of the discrete, these are what we call characteristic modes. And the system left just to its initial conditions responds as through a linear combination of characteristic modes. Characteristic modes are in the form of gamma to the n, where gamma is the solution of your characteristic equation, which is characteristic polynomial equal to 0 equation, and characteristic polynomial is the polynomial that is formed from the operators E on the left-hand side of the difference equation. There are repeated roots. That's a second case, case 2. Some of the roots repeat. So, in other words, your Q of gamma is in the form gamma minus gamma 1 to the r plus gamma minus gamma r plus 1 all the way to gamma minus gamma n. This is just factoring your characteristic polynomial, and what we're trying to say is there's a root gamma 1 here which repeats r times, and all the others are simple roots. If that's the form of your characteristic polynomial, then your zero input response is in the form C1 plus C2n plus and so on, CR n to r minus 1, gamma 1 to n, and then you have CR plus 1, gamma r plus 1 to the n, plus Cn gamma n to the n. So now, for the root that repeats r times, you have this polynomial in n that multiplies the characteristic mode gamma to the n, and then you have the simple roots which just give their own characteristic modes. And then case 3, we have that complex roots. Just like in the case of a continuous time system, we're going to restrict ourselves to the cases where A's and B's are real. In a particular case here, we assume that A's are real. If A's are real, then this polynomial Q of gamma is the polynomial with real coefficients. And what we know for polynomial that has a real coefficients, if gamma is the root of that polynomial, gamma complex conjugate is the root of that polynomial. That's very easy to demonstrate. So if you now assume that you have a root, let's say gamma 1, which I'm going to write as magnitude of E gamma e to the j beta, and you say this is a root of your characteristic polynomial, Q gamma is equal to 0, then it has to be gamma 1 complex conjugate, which is again magnitude of gamma e to the minus j beta, also root of Q of gamma equal to 0. The complex roots of the real polynomial, they travel in pair, right? The root and its complex conjugate. In general case though, you got to be careful. In general case, this may not be situation. If these A's are complex, then there is no restriction. You can have a root that doesn't have its complex conjugate as a root. In that case, still case 1 and case 2 are applicable, but the case 3, may not. So So in general case, these two, 1 and 2, are always valid. Because in these two, we put no restrictions on what gammas are. They are either simple or repeated. But they can be either real or complex. Now, if I know that the roots come in pairs, then I can put them together and get some insight in what does the output of the system look like. And let's do that. So in this case, y0 input of n becomes also a linear combination. So it's C1, gamma 1 plus C2, gamma 1 complex conjugate. But to the end, sorry. To the end. But this can be written as C1 magnitude of gamma e to the j beta to the power of, that's the first gamma 1 root to the n, plus C2 magnitude of gamma e to the minus j beta to the power of n. And you can see right away that this can be significantly simplified. For example, gamma to the n can be taken outside as common. And then what I'm left inside is C1 e to the j n beta plus C2 e to the minus j n beta. And then using Euler's rule, I can say that this is C1 cosine n beta plus C1 j C1 sine n beta plus C2 cosine n beta minus j C2 sine n beta. I just using Euler's rule. And then if I define C1 plus C2 as a new constant k, and JC1 minus JC2 as a new constant K2, then I can rewrite this whole thing as gamma to the power of n, K1 cosine of n beta plus K2 sine of n beta. And I can take it even one step further. If I have K1 cosine plus K2 sine, I can write this in terms of the magnitude and phase. So I can finally rewrite this as a C gamma to the n cosine n beta plus theta, where this C is going to be square root of K1 squared plus K2 squared, and this theta becomes minus arctangent of K2 over K1. But really, this is just academic, because all we really seek to find is the format of this output. There are still these constants C and theta that we would have to determine. How would we determine that? We would determine them from the initial conditions, right? This system as a whole carries this as its signature the format of its characteristic modes. It's in this Q of gamma, right? But the same system will have different outputs depending on what the initial conditions are for that system, right? The only thing that I can say about a given system is no matter what the initial conditions for that system are, the output of it is going to be a linear combination of characteristic modes. I will always be able to mix characteristic modes appropriately to form the output, right? And how I mix them, it will depend on what the initial conditions were. So it will always be some C's and some thetas that will depend on what particular initial conditions were. But the beta and gamma are going to be the signature of the system itself, because they're going to be roots of the characteristic of polynomial. they can be ultimately traced all the way to the difference equation that describes this particular system. Okay, so that's a good chunk of theory. So let's go through a couple of examples.
Excuse me, sir.
Go ahead.
Yeah, if we have a parallel equation with 6 roots, 2 complex, 2 distinct, and 2 real, so what would be the form of the y-output?
It's going to be it's going to be a linear combination of its characteristic modes. Let's just look at directly your question. So here's what his question is. I solved Q of gamma, and I came up with, I believe you said six roots. 2 of them are distinct. Gamma 1 and gamma 2. Gamma 3 repeats 2 times, right? And gamma 4 and actually gamma 5 and gamma 6 complex conjugate, right? So I have 2 real roots, which are simple roots, 1 real, which repeats 2 times, and then I have 2 complex roots. So then I can write the form of my zero input of n as C1 gamma 1 to the n plus C2 gamma 2 to the n plus C3 plus C4 times n gamma 3 to the n and plus C5 gamma 5 to the n cosine of n times the angle of gamma 5 plus a. So that's the format of the output. And by observing this, let's say you hit, we'll do that. Let's say you excite your system and it has some non-zero input conditions, and you let it settle down. By observing how does this output behave, you can kind of deduce what kind of roots it has, what kind of roots the characteristic polynomial will have. Okay? So let's go through a few examples. So this is example 310, and we're considering a system yn plus 2 yn plus 1 minus 0.16 y, and is equal to 5 x of n plus 2. We have the following initial conditions. Y minus 1 is going to be 0. Y minus 2 is equal to 25 over 4. So how do we determine the zero input response of this system? Let me see, make sure that I follow my notes. I actually say there are 2 steps. So step 1, you form the characteristic equation. And this is really very easy to do. All you need to do is look at what's on the left-hand side, and then based on what you see here, use that as the power of your gamma. So characteristic equation becomes gamma squared minus 0.6 gamma minus 0.16 is equal to 0. Right, so that's your characteristic equation. N is equal to 2 in this case. Therefore, we'll end up with 2 roots. Right, so we solve this quadratic equation. Gamma 1, 2 is going to be 0.6 plus minus square root 0.36 plus 64 over 2. So gamma 1 is equal to 0.8. Gamma 2 is equal to 0.2. So your y of n zero input of n is in the form C1 0.8 to the n, and then plus C2 minus 0.2 to the power of n. So that's a step 1. Step 2, there will be some constants here that need to be determined from the initial conditions. Applying initial conditions here for minus 1 is equal to C1 times 0.8 to minus 1 plus C2 minus 0.2 to minus 1. This has to be equal to 0. And then y zi of minus 2 is going to be C1. Okay, that's switched here. So C1, 0.8 to minus 2 plus C2, 0.2 minus 2 is going to be equal to 25 over 4. Okay? And this is 2 equations with 2 unknowns. We know how to solve that. Let me just write what I have here. It's minus 0.2 to the minus 1. Or actually, let me just do this. 0.8 minus 1 minus 0.2 minus 1, 0.8 minus 2 minus 0.2 minus 2. And then here, C1, C2 is equal to 0, 25, 4. This is system of equations of 2 equations of 2 unknown. And at this stage, just a remark for the exam. At this stage of your schooling, I assume you all know how to do this. So all of you have calculators that have solving capability to do this. Right? So find out on your calculator how to solve systems of linear equations. I mean, you can do this manually, and I trust you can do it. And I trust if I give you a little bit more time than what's allocated on the exam, you're always going to get correct solution. But the problem with the exam is always time. So in preparation for the exam, find out how you do this on your calculator so that you can do it in one step. Here I use MATLAB, and to obtain that C1 was equal to 0.8, and C2 was equal to 0.2. So therefore, y 0 input of n, in my case, in the case of this problem, was 0.8 times 0.8 to the power of n plus 0.2 minus 0.2 to the power of n. And this is true for n greater or equal n is 0. Go ahead.
Excuse me, sir. I think the root, under the radical sign, it should be 0.36 plus
0.64, yeah. Yeah, 4 times this times this. 4 times 0.16 is 0.64. Yeah. Right. And then this is 0.36 plus 0.64 is 1. Square root of 1 is 1. 0.6 plus 1 is 1.6 divided by 2 is 0.8. And then minus 0. This is minus 0.4 divided by 2 is 0.2. And you're right. But the rest of it is the theorem of the known result. If I know the result, I can always get it, right? No matter how many mistakes I make along the way. Any questions here? This is very similar to what we did for the continuous time system. So let me, I guess the time is up, so let me stop here. Maybe give you some, I'll do a couple of more examples next time, but let me still give you problems that are related to this material. So that you don't have to wait for me to just go into problems. So problems 3.48, 4.9, 4.11, 3.5.1, 5.2, 6.4, 6.5, and 6.7. So they're all exercising this material. We're going to go through a couple of examples next time that that have complex roots and repeated roots, so that idea how to solve for those. Okay.